Hello everybody, welcome to week 11, which will be our last week of new lecture content. So we have two themes this week. First one is normal subgroups and the second one is quotient groups, and both are closely related. So our first installment will be about normal subgroups. So we've seen this concept already during the second homework sheet, but let's just recall it. And also in this lecture we'll talk about why it's important, and we'll see that also in the second round this week about quotient groups. So a subgroup N of a group G is normal if for every element of the group G, the left coset and right coset of the subgroup determined by that element are the same set. Okay, and the notation for that is this sort of triangle with a little stroke under it. This says N is a normal subgroup of G. So this is kind of a technical property. The reason why it's obvious, or why it's interesting, is maybe not obvious at first glance from the definition. We'll see the full scope of that in the second lecture this week. An equivalent version of the definition, which in many cases is more easy to use and maybe more easy to recall, is to say that a subgroup is normal, a subgroup N is normal in G, if whenever you have an element N of the subgroup and you take any conjugate of that element in the group, that you still remain within the subgroup. Okay, so basically a subgroup is normal if it contains all the conjugates in the bigger group of all of its elements. So in other words, if the subgroup is actually a union of conjugacy classes, some of the conjugacy classes of the group. So using that interpretation of the definition of normality, for example, one can see that the center of a group is always a normal subgroup because it consists precisely of those conjugacy classes that only have exactly one element in them. Okay, so the first observation here is to observe why it is that these two definitions are equivalent to each other, that they capture the same property of a subgroup. In terms of which definition to use, it doesn't matter. They're equivalent logically. In some cases, one or other of them is more useful in certain circumstances, in certain examples, or so on, to decide whether a given subgroup is normal or not. But it's kind of useful to have both of those definitions at your fingertips and be able maybe to move between them if you want to, as appropriate. So to see that the second version is a consequence of the first one, suppose we have a subgroup N that satisfies the first version of the definition of normality. So that Gn is equal to Ng, the left coset and right coset determined by every element G are equal to each other. And let's say that we want to show that it then follows that this subgroup N contains all the conjugates of all of its elements. So let's give ourselves an element N of N. Okay, if we look at the product Gn, for some element G of the group G, it's in the left coset because it's G multiplied by an element of N. If the left and right cosets are equal to each other, that means that Gn is in the right coset also determined by G, so it's equal to N dash G for some N dash in N. And just rearranging that equation by multiplying both sides of it on the right by the inverse of G, we can observe this is saying that Gn G inverse is equal to N dash, so it belongs to N. And the conjugacy class of N is contained in N. Okay, so if our group N satisfies the criterion in the first version of the definition of a normal subgroup, then it also satisfies the condition in the second one. See that the first is also a consequence of the second. Well, suppose we have a subgroup N that is a union of conjugacy classes, so it contains all the conjugates of all of its elements in the group G. And let's give ourselves an element G of the group. So we must show that the left and right cosets of N determined by G are equal to each other. Well, why would that be true? We know for every little element N of N, that Gn G inverse belongs to the subgroup N. And that's saying that Gn is equal to something in N composed with G inverse. So Gn is equal to N dash G, which is saying exactly that Gn is an element of the right coset determined by G, the right coset of N determined by G. Then the left coset is contained in the right coset, and the same argument, if we start with G inverse Ng, which is also a conjugate of N, shows us that the right coset is also contained in the left one. So these are two equivalent characterizations of the concept of normality for subgroups. They're sort of equally important, they've equal status. Occasionally one or other of them is kind of more convenient to use, and both of them are sort of I think thinking about the reason why they're equivalent will probably help you to get a good handle on the concept of a normal subgroup. Okay, a few examples. Well, every group is a normal subgroup of itself, and the trivial subgroup is a normal subgroup of every group. Those two conditions are easily checked no matter which version of the definition you take. Every subgroup of an abelian subgroup group is normal, and remember, conjugacy classes in abelian groups are just single elements, and certainly every subgroup is a union of single elements. Any subgroup that's the kernel of a group homomorphism is normal, and we will see the reason for that in a couple of minutes. We looked at D6, the dihedral group of order 6, back in the second homework sheet. In D6, the subgroup consisting of the 3 rotations is normal. That's something that you can also check for D8 or any other dihedral group. The subgroup of rotations will always be a normal subgroup. If we take the subgroup consisting of, I should say, of any one reflection and the identity element, that is non-normal always in the dihedral group. Okay, and finally, this is one to think about. Any subgroup of index 2 in any group is always normal. And there are plenty of other examples around. So basically, if you're thinking about this concept, it's sort of a good habit is to think whenever you encounter a situation where you've got something that's a subgroup of another group, you can ask yourself, is it normal? And you can ask yourself questions like, if you take the centralizer of an element in a group, is it going to be a normal subgroup? If you take the stabilizer of some element for a group action in some group, is that going to be normal? Okay, can you make any deductions about that? Okay, one of the assertions there was that the kernel of a group homomorphism is always a normal subgroup. So let's see why that's true. And let's recall from last week that if we have a homomorphism of groups, in the first instance, what that means, if phi from G to H is a homomorphism of groups, that means that phi is a function from a group G to a group H with the property that it respects the group structures, that it's compatible with both group structures. And what that means is if I take a pair of elements in G, compose them with G, and then apply phi, I land somewhere in H, that should have the same outcome as if I map my two elements of G into H separately under phi, and then do the composition over in H using the group operation of H. So if those two processes always result in the same outcome, the function is a group homomorphism. Okay, so let's write N for the kernel of phi. And let's recall what that means. The kernel of phi is the subset of G consisting of all of those elements whose image under phi is the identity element of H. We know it's not empty because we proved last week that it contains the identity element of G at least. And we know also from last week that the kernel of phi is a subgroup of G, it's not just a subset. Again, the assertion here is that this subgroup of G is in fact a normal subgroup. So let's see why that would be true. And again, here we've got two choices. What do we have to do? We have to show the subgroup is normal. We can either do that by showing that for every element of the group, the left and right cosets that it determines are the same set, or we can do it by showing that whenever we have an element of this subgroup, that all of its conjugates in G are in the subgroup as well. So we use the latter approach, although for this particular instance, either is quite usable and it's a nice exercise to do it using the other one. Okay, we want to show that N is normal in G. This is our setup. To do that, we should give ourselves an element of N, and we should show that each of its conjugates in G is also in this subgroup N. We know how N is defined. It's defined as the kernel of this homomorphism phi. So let N be an element of the subgroup N. What we need to show, and here for kind of explicit clarity, I've written the group operation of G as star G. If you want to just write Gn, G inverse here, that's absolutely fine. What we must show is that for every group element G of the domain G here, that Gn, G inverse also belongs to this subgroup N. What we have to do to show that something is in N is show that its image under phi is the identity element of H. So to show that this element is in N, we better apply phi to it and hope that we can show that what we get is the identity element in H. Well, if we apply phi to G, N, G inverse, phi is a group homomorphism. That means it respects the operation of G. It transforms it into the operation in H, really. So the image of this element should be the image of G, composed in H with the image of N, composed in H with the image of G inverse. Now, N is not just any old element of G. It belongs to the subgroup N of things whose image under phi is the identity in H. So phi of N is the identity element of H. Okay, that's because N is in the kernel of phi. So this middle term here in this product of 3 is the identity element in H. That means it acts neutrally in H, so we can just sort of ignore it, leave it out, and say that this product of 3 things in H is just phi of G composed in H with phi of G inverse. Phi is a group homomorphism. So phi of G composed with phi of G inverse is just phi of G composed with G inverse, phi applied to G composed with G inverse in G. That element of G is the identity element of G. When we apply phi to that, we know, again, from last week's reasoning about homomorphisms, that we get the identity element in H. So the conclusion is, the mapping phi, the homomorphism phi, sends a conjugate of N to the identity element of H. In other words, every conjugate of N belongs to the kernel of phi. Okay, and the conclusion then is that because N, the kernel of phi, is a subgroup of G that contains all conjugates of all of its elements, it is a normal subgroup by definition. So the kernel of a group homomorphism is always a normal subgroup of the domain. Okay, it's not just a subgroup, it has this extra additional property of normality. And why that's important, we have kind of already seen last week, but we haven't put all the pieces together yet. And that's what we'll do in the next section. But basically what it allows us to do is essentially construct a group whose elements are the cosets of the normal subgroup in the whole group itself that we started with. And that gadget is called a quotient group. So that would be the content of the next item. The challenge, meanwhile, for this first part of week 11 is to prove that assertion from earlier on there, that any subgroup of index 2 in a finite group is normal. And just bear in mind, a subgroup of index 2 in a finite group is a subgroup that consists of exactly half of the elements of the group. So for example, a typical and kind of nice example is the subgroup of any dihedral group that consists only of the rotations. That's a subgroup of index 2. And the assertion is that any subgroup of index 2 is normal, and your challenge is to prove that. So I guess a hint would be that I think, well, for me, version 1 of the definition of the normal subgroup is the one that's easier to apply here. And what you really need to think about is, with a subgroup of index 2, what the setup can be in terms of writing the group as a union of separate distinct left cosets or separate distinct right cosets, and ask yourself, how different can they be from each other, because there's so little room for maneuver. You've got a subgroup that already takes up half of the elements of the group. So have a go with that, and meanwhile we will update with the second round about quotient groups. Thank you, everybody.